Hello, welcome to Shop Talk Live, the Aluminum series. Tonight we're going to be talking about intermediate TIG. My name is Andrew Pfaller, and I'm going to be covering a couple different concepts tonight that we get a lot of requests for. Certainly if you have any questions, submit them via the email shoptalklive@millerwelds.com, and we'll try to get those questions answered for you. Tonight we're going to talk about four main topics that have an impact on your aluminum. So a couple weeks ago we talked about the basics of TIG welding and some of the settings you might want to use, some of the things you might want to do to adjust in the machine, and we also talked about material preparation. Tonight we're going to be taking that one step further and hopefully advancing your knowledge and your ability to perform and make excellent TIG welds with your power source. When we think about TIG welding, there's four main factors that we're going to be kind of bringing in as the next steps. The first one is going to be tungsten. We're going to be talking a little bit about balance. I know we've talked about balance and where you might set it in the past, but tonight we're going to get into and try to explain some of the fundamentals and the theory behind why we make some of those changes. We're also going to talk about frequency, and then getting into a topic that is very popular with a lot of viewers, and that is the different waveforms that we have available in, for example, the Dynasty DX power source that we have here tonight with us. So I'm going to go ahead and get into some of this. Just to start, I want to show some of the resources that we have available that's very useful as a welder to have on hand in your facility next to your welder. It's these quick reference guides that we have put together. These are available. You can download these as a PDF free of charge from our website. Go to the Dynasty product pages. There's a lot of the fundamentals that we go through and are going to be going through not only tonight, but in the series next week on Wednesday, June 15th. That gives you some good starting points, gives you some explanations of a high and a low setting. But again, we're going to cover some of this a little bit more in detail tonight. One of the things that, like I said, that we want to start with is talking about and it has an impact on your welds is going to be your tungsten. So there are a couple different tungsten types that are available when we're welding on aluminum. The two most common ones that we recommend with welding equipment that's used in the industry today, so the modern inverter-based power sources, is going to be the 2% seriated and the 2% lanthanate, so the gray band and the dark blue band. There is a couple different tungsten types available in the industry. You see some of the purple, you see some of the light blue or the aqua, the tri-mix tungstens, and then some people you'll hear talking about the 2% thoriated. But by and large, if you are welding aluminum, these two that we have here tonight are going to be the tungstens that will work for not only an AC application, but also a DC application. So it's a great all-around tungsten that can help you standardize in your shop. Some of the things that we want to talk about is in relationship to the tungsten, not only the types, but also the different sizes, some of the settings in the power source that can have an impact when you're using it in relationship to the different sizes of tungstens that you might put in the front of your torch. So let's go ahead and get into it. I think probably one of the first fundamental things that we want to talk about, again going back to the different tungsten types. Some people that are welding on aluminum ask me a lot, why do we, what type of tungsten should we be using? I've got the green stuff, can I still use that? The answer is, if you have a transformer-based power source, like an old Syncrowave, an old Aerowave, those power sources will work with the pure tungsten, and you would pre-ball the tungsten, which we'll get into, and I'll draw some images here on the tungsten geometry. But the pure tungsten has a lower melting temperature. So if you think about when we're actually sharpening our tungsten, and you bring it down, you put a truncated end on that, and you start throwing heat at this with a transformer-based power source. What ends up happening is this tungsten will end up melting back and forming more of a ball shape on the end of your electrode. Now, that can have, when you're trying to weld thin aluminum or maybe like a fillet weld, that can have an impact on your ability to put the weld where you want it to go. And so not only the tungsten type, but we'll talk later tonight about the AC frequency and how that can have an impact on the welds that you're trying to make. The reason why on the modern inverter-based power sources like the Dynasty, the new vintage of Synchrowaves, and even our diversion products, the Multimatic 220 AC/DC, we recommend the 2% seriated, is because if we take and put a truncated tip on the end of that tungsten, the modern inverter-based equipment will simply round these small corners here off, and we don't get that large ball shape like what you'd get with an older transformer-based power source. So when it comes into directional control and getting the weld placed where we want it to, this can have a huge impact on your ability to perform maybe a small weld or a weld on thin material successfully. The 2% seriated, or the 2% lanthanated for that matter, which is the dark blue that we talked about, has a little bit better ability to emit the electrons and also resist the thermal shock of not only high amperage applications, but also when we're welding on aluminum, the dark blue performs very well. I had mentioned the gray tungsten, the 2% seriated. This is a good all-around tungsten that will work not only, like I said, in the DC applications, so steel, stainless steel, but also in aluminum without really changing your tungsten preparation. For an all-around welder that maybe is getting into it or trying to grow their skills, the 2% seriated is going to work very well. The 2% lanthanated does give a little bit finer arc starting performance, but it is a little bit more expensive. So for somebody that doesn't necessarily have a highly refined skill or eye to see what's going on in the arc, this is probably just adding some undue cost that isn't necessary to be successful. So I wanted to get in and talk about the sizes of tungsten electrodes. So you can see here we have 3 different sizes that I have examples on tonight. And what we have is a 1/16, a 3/32, and an 1/8 inch. And you're probably wondering, well, when would I pick maybe a smaller diameter or a larger diameter? And really the key behind this is going to be the amount of heat. So tungsten electrodes take a certain amount of heat in order to start the arc. So if you're using a foot pedal, which is very common in North America here, we start the arc and we need a certain amount of heat preheating the surface of this tungsten in order for it to start emitting those electrons off of the surface. And if we go to a larger tungsten diameter, so maybe like an 1/8 inch tungsten diameter, there's a lot more thermal mass to pull away the heat from the tip of the tungsten, and is going to end up giving, if we don't make any setting changes in the machine, will give us restrikes or that pop, pop, pop that you might experience without actually starting a nice stable and generating a nice stable arc. Now, one of the keys here is if we use a small tungsten diameter, there's also the adverse effect, is the power source may be putting out excess amounts of heat at the start of the arc and causing the tungsten to actually deform. And what happens is if you're using a very small diameter tungsten, you will actually overheat the surface of the tungsten on the end here and transfer tungsten droplets into into your workpiece, which is, if you're doing X-ray quality work or working to any codes where you're going to be doing X-rays, that will pop up and show on an X-ray like night and day or black and white, no pun intended. So one of the keys here is use an appropriate size tungsten for your application. The rule of thumb that I recommend is don't ever use a larger diameter tungsten than how thick your material is. If you're using material that's, say, 1/16 of an inch, you really shouldn't be using over a 1/16 of an inch diameter tungsten. And then also you want to make the appropriate changes in the parser. So I'm going to go through here quick and just show for the audience how we make those selections on the Dynasty DX interface. So we look at 2 different buttons here. So the A button in the upper right-hand corner and then also the second in, which is your gas dig button. We're going to push those two just simultaneously and just do one quick press. And you can see here there's different tungsten selections, both metric equivalents and our US equivalent or our US variants here. So we have tonight, we'll get into some different examples later with some different tungsten diameters. So we're going to start off with a 3/32 tungsten diameter, and then to get back out of that, we simply hit that amp and the gas dig button. It says menu off, and we're right back at the main screen. One of the last things that I want to talk about is the actual tungsten grind angle. This is probably more relevant for a DC application, but it certainly is relevant for an AC application. So we talked a little bit about using an old transformer based and having a bald tungsten and using the truncated tungsten on aluminum here with a modern inverter. I want to explain why we would maybe want to put a truncated tip versus just a purely pointed tip. If we have a long pointed tungsten and we have heat being generated down here on the tip, what ends up happening is the electrons are emitting perpendicular to the surface. A lot of people think that the electrons flow kind of down the surface of the tungsten. They actually come off perpendicular to the surface and then kind of curve down towards our plate. So if you have this really fine point on the end of your tungsten, not only can you not see the tip of that tungsten in that bright plasma column at the end of the tungsten, but there's also not a lot of surface area. There's not a lot of mass to pull that heat away. And so you can end up creating a small ball on the end of the tungsten, which now, instead of the electrons being kind of emitting perpendicular down at the plate, they're emitting more parallel with the surface of the plate and coming out more, use a different color here, coming off more sideways. And especially in a fillet weld or a T-joint application, that's going to make it want to wander to the side plates more so than if you have a more truncated tungsten. So if we draw more of a truncated tungsten, you can kind of see what I'm talking about. We put a little bit of a flat spot on the end. That gives us more mass, more surface area for those electrons to emit from. Those electrons are actually going to emit right off of the tip of that tungsten. And then also, you're still going to get some coming off the sides, but because of the surface area of this flat spot on the end of your tungsten, you'll get a little rounding on those corners. And what's going to happen is you're going to get a much finer arc column than if you have a long tapered tungsten or a bald tungsten on the end of your electrode there. Okay, so I think that covers the tungsten electrodes quite thoroughly. The next topic that I want to cover is our balance settings. So balance settings are something that comes into play, and we get quite a few questions on, and I think that we can spend quite a bit of time talking about the theory here. It's quite important because this is one of the primary characteristics of the primary settings and a welding power source that's available whether you have a modern inverter base with extended balance ranges or an older transformer based. Even back to the 70s, we had balance settings in the Sacred products. So it is something that's relevant to people of all different machine types, with the exception of a couple that maybe have a fixed setting to help reduce operator confusion for maybe somebody that's really a beginner welder. So what is balance, you might say? Well, balance is going to be our ratio or time that we spend in electrode negative versus in electrode positive. And this is a pretty important topic because this can really impact the quality of your weld. I'm just going to draw a couple things on here, electrode positive, electrode negative. So if we think about an old transformer-based power source, you actually had what would be a 50-50 balance. So you had 50% in electrode positive, and you had 50% in electrode negative. With the invention of the sync wave power sources, we were able to skew this, you know, slightly one way or the other, and typically you could get up to about 68%, you know, electrode negative, which it helped the welder, but it really wasn't as good as what we can get with the modern inverters. So the ratio that we generally use now, or the balance setting that we generally use now, is going to be 75% electrode negative, which the balance or the resulting mass comes out that 25% of the time we're in electrode positive. And so for those that are maybe not familiar with this, electrode positive is going to be our oxide etch. And this down here, some people refer to the electrode positive as more the welding side of the cycle, and that's because in this, 70% of the heat, roughly, now this is just using some rough math, 70% of the heat is down into the workpiece. Up in electrode positive, about 70% of the heat is in the tungsten. So you're probably saying, okay, this is starting to make sense here. When we're in electrode positive, up here, what that's causing is 70% of the heat is on the tungsten. So if we think back to that tungsten geometry that we just drew, what happens is if we were welding in straight electrode positive, you're going to end up with a pretty large ball on the end of your tungsten. And when we're in electrode negative, it promotes more of a sharp tungsten. So 50-50 is kind of the starting point. Some applications you may, you know, if you're using an old transformer-based power source, you want to pre-ball the tungsten, you may skew that down to like a 40% balance setting, or even on the Dynasty products, we have a 30% which is labeled ball, or 30% balance. And that's to pre-ball the tungsten for maybe somebody that's doing high amperage overlay applications. But for the most part, you're going to want to be up above 50% balance. Now, what happens is if we get too high of a balance setting, if we were to skew this thing all the way over to maybe like a 95% balance setting, what happens is you start, and this is kind of a top view of a weld, you start seeing these oxides that aren't getting etched off of the weld, that are getting left on your part. And those oxides are very hard. It's actually considered a ceramic. You think about grinding discs. A lot of times they're an aluminum oxide grinding disc, because oxides, those aluminum oxides, are extremely hard, considered a ceramic. And if we don't have that electrode enough or a sufficient amount of electrode positive, those oxides aren't getting etched off of the surface of the material. So we talked, you know, in the material preparation session about, you know, using a wire brush and doing some different methods that help to eliminate or reduce the amount of oxides on the surface before we even start welding. But those oxides start forming immediately when exposed to oxygen in the atmosphere that we breathe. So we have to have, even if we did our wire brushing and our cleaning material prep properly, we still need to have the electrode positive portion in most applications to be able to read the welding puddle and to be successful with that. So one of the questions that came in was asking, if I have peppering, what do I do? If we have peppering in the welds, we don't want to turn the balance setting up, because that's giving us more electrode negative, which is heat in the work, and less oxide removal. We need to turn our balance setting down, which increases this amount of time, and that electrode positive portion is going to give us more of that kind of hazy etching zone along the edges of the weld, which in most codes and specifications is required to have you know, some of the etching zone visible on either side. Some of them actually call out a minimum, you know, measurement that you have to have at the toes of your welds in order to be considered an acceptable weld. So the balance setting on the Dynasty power source is a column all the way on the right-hand side. So if we look at here, it's going to be this, this setting here. We click in. It says balance. Right now it's set to the Pro set. And we can turn this down if we want more oxide or more cleaning, oxide removal or cleaning. And we turn that up. You can see here the Pro set is at 75%. That's an excellent starting point. If you've done your material prep properly, that's a great starting point to continue working with. If you have really good clean material, trying to get a little bit more heat into the part, you may turn that up if you want to kind of reduce those etching zones. But for the most part, probably about an 80% balance range is going to be the maximum of what we typically see in the industry. 75% down to 68% is that average that we see most people being in. Okay, so the next thing that the next topic that we want to cover tonight for the intermediate TIG is going to be the frequency setting. So just kind of in summary before we dive into that, the big takeaway here: balance setting is used for oxide removal and puddle cleanliness, assuming we've done our part prep. Turn the balance setting up until you get, or if you start seeing peppering in the welds, then we'll turn the balance setting down. So you can turn that balance setting up pretty much until you start seeing that peppering in the welds, assuming you haven't completely eliminated these white etching zones on the sides of your weld. Not to be used necessarily as a heat input control or anything like that. Mostly used to control our oxide removal. So frequency. Frequency is one of the most widely used parameters that are the most readily visible parameters when it comes to a welder or a welding operator. Somebody developing a welding procedure would maybe want to consider utilizing this in order to get certain characteristics and help them make the weld easier for the actual person doing the weld. So AC frequency. I'm going to go right to the top of the paper here. AC frequency, so balance is the amount of time or the ratio that we're in electrode positive versus electrode negative. AC frequency, all we are doing is, if this is our electrode positive and electrode negative side, we are not changing the ratio of how much we're in electrode positive versus electrode negative. We are simply so if you were to compare these two, this one on the right-hand side, twice the frequency is the one on the left-hand side. Still the same amount of area in this box, these two boxes, as there is in this box. And then if we look at these two boxes up here in blue on our electrode positive, those equal the same amount of area there. So the balance or the ratio of our time in electrode positive versus electrode negative hasn't changed. The amount of area hasn't changed. We're just simply hitting more times and switching, crossing this zero crossover point, changing polarity directions more frequently. Hence, kind of the name where frequency comes from. So one of the big questions is what impact does this have on my weld? Now, a lot of transformer-based power sources or traditional style equipment is going to be a slower frequency, more like on the left-hand side here, and that's going to be a 60 hertz. That is largely driven because your input power off of your wall is 60 hertz in North America. There's some parts of the country run off of 50 hertz. North America here, 60 hertz. When we have a 60 hertz output, coming off the wall, comes into the back of a transformer power source, we're generating opening up a magnetic field in that transformer. That field is collapsing when the AC input power changes directions, and so it's expanding and collapsing magnetic fields. We're simply taking it from a high voltage, low amperage, and transforming it into a low voltage, high current setting on the output side of the welder. And so we're really tied and confined to that 60 hertz. Can't really do much with it. The way I'd like to describe this is like you take a piece of pie and you cut it into 60 bites and you try to swallow those things without chewing them. You're probably going to end up choking. It's a lot of bigger hits. If we come over here and say this is double the frequency, this is 120 hertz. This is going to be more like your inverter-based power source. So the Dynasty products come, factory default, or the Pro set is going to be at 120 hertz. We can actually get up to 400 hertz on our welding output with the Dynasty products. And so the impact that this has for us is most visible on low amperage applications and applications where we're doing maybe like an inside corner joint like this. So if we have our gas cup up here and we have the tungsten sticking out, what happens is electricity wants to take the path of least resistance. So the path of least resistance here is going to be straight to that plate and straight to this plate. And anybody that's welded on aluminum in a T-joint configuration like this, especially at low amperage, knows exactly what I'm talking about. You start the arc, you start getting some superficial melting here, you try to turn your torch a little bit, point it more at the bottom plate, the arc completely jumps across and you're melting down here. It's very hard to get in that bottom of that corner and actually get the weld placed where we want it to. And that's because there's very little, for lack of a better term, momentum or arc pressure off of the end of that tungsten to drive the electrons to the corner. They want to take path of least resistance, which is straight to the, perpendicular to the surface of the plate. So what ends up happening in this case is you maybe throw your filler metal in there, and we'll try to demonstrate this later if we have time. You end up throwing some filler metal in here, and you get a weld bead that looks something like this. Now, what do you see wrong here? We didn't consume this root of this weld or have fusion all the way to the interfaces of those two parts. That's a big no-no when it comes to welding inspection and destructive testing. If we're doing like a procedure qualification or trying to actually make production parts, if they get x-rayed or something like that, that's going to show up and cause problems for us. So when we are turning our frequency up more to this side here, 120 to 400 hertz, that starts getting us some nice arc pressure off of the end of our tungsten and helps drive that arc right down into the bottom of that corner. And that allows us to get a weld that's, consumes the root of that joint or the interface between those two surfaces, and then also get us, a more appropriately sized weld. I want to talk about appropriately sized welds because I think this is very important as it pertains especially to fillet welds. If we think about putting a weld in here, and the metric equivalence, the metric system makes this very easy, so I'm going to use the metric equivalence because it makes the math a lot easier. So you can see on the drawing that I did previously, the one weld is, roughly twice the size as the blue. The red weld here is roughly twice the size as the blue weld. Not quite, but just for math's sake, we're going to say it's twice the size. If we have a 3 millimeter, which is 1/8 of an inch, and then the other one is a total of 6 millimeters. And the other leg size is the same, so we have a 3, and then this is a 6 down here. And I'm going to draw it just because it makes it really easy to count if you're more of a visual learner than a mathematical learner. Our blue weld is going to be our 3x3 leg sizes. So just doing some quick math, the area of a triangle is 1/2 base times height, which equals 1/2 3 times 3 equals 9/2, or 4.5 millimeters squared. If we look at the larger size here, we have 1, 2, 3, and then certainly your other one, which is 4 times the amount of filler metal going into this larger joint or larger weld than we do the smaller one. So again, 1/2 base times height equals 1/2 times 6 times 6 equals 36/2 equals 18 millimeters squared. So you're probably thinking, well, that's not, these are relatively small weld sizes, 1/8 inch versus 1/4 inch, whatever. It's not going to have a huge impact on my operations. Filler metal spend isn't drastic for us. The thing that come into play here is there's a lot more factors than just your pure filler metal spend. Certainly that is important, especially in today's day and age when all of the costs are rising. We're trying to control costs. The filler metal spend certainly is a portion of your bottom line that you want to be controlling, but it also has a huge impact on the speed that it takes. If you're a welder, you having to manually be feeding that filler metal into the puddle, so now you have to feed 4 times as much to get that joint done. It's more gas. There's a lot more heat goes into the part. We covered this in the past. The heat affected zone on aluminum is actually where your weld is typically going to fail. So more heat into the part, your heat affected zone out here in your base material is going to be a lot larger because more heat input into the part, and give you a larger annealed area in the material that is going to cause a larger weak point, not give you as much structural integrity. The other thing that we want to consider is the actual distortion. As welders, we know that distortion is very critical in order to be successful. If we have to weld subsequent things onto it, or it has to fit into a fixture, or fit into a final application, you put your parts together, start welding it, stuff starts pulling, and that can cause problems. This is going to pull along that surface of that face of that weld. And you can see here, this one here, it's about twice as much pull at the surface of this because of the distance here than if we do the smaller weld. That means twice as much distortion, twice as much straightening. Straightening and post-weld operations are, in many cases, a significant portion of a company's welding operations and labor spend. So as a manager, as an owner, even as a welder, that's why frequency is very important to making sure we get an appropriately sized weld. Now, I do want to provide some recommendations because we do get questions about, when would you want to use a lower frequency versus a higher frequency. So the lower AC frequency, so maybe like a 70 to a 90 hertz. This is going to be for maybe like an overlay application and high amperage. The reason for this is when we're making all of these transitions back and forth between electrode positive, electrode negative, if we have a high amount of inductance or resistance in our welding circuit, so inductance is caused by coiling up of welding cables. It's a lack of a better term, an electrically induced resistance in the welding cable. You might not actually be getting the waveform and the welding characteristics out at the torch that the power source is putting out thinking is making it to there. So a low amperage application and thin materials and inside corners you're going to want to be for sure 120 plus, and then for handheld applications I generally recommend up to about 250 hertz. And the reason for this, and my rule of thumb, is your AC output frequency. So, you know, whether it's a low frequency or high frequency, should be inverse of your welding amperage. So if you're using a high welding amperage, do a lower frequency. So maybe in that 70, 90, maybe up to 120 if you're like at 400 amps. If you're doing thin material, you want to use that higher frequency, that 120 to 250 hertz range, because that helps get you that directional control, that push that we talked about here at the beginning of this topic, to drive the electrons down into the corner of that joint, or help track you if you're doing maybe like a butt joint type application. So where do we set this on the power source? The same button on the Dynasty that gets you into balance is also going to get us into the frequency. Just hit it one more time. The label down here, it says AC frequency, and then you can change this appropriately depending on which way you want to go, up or down. Now again, the pro set, or our starting point, is going to be at 120 hertz. That's a great starting point. A lot of power sources are actually fixed to 120 hertz. We have some of our power sources that are fixed at 70 hertz because they're a little bit higher amperage application, and it's not necessarily intended for people to be adjusting those parameters because the type of work that they do, or maybe their skill set, their operations are designed more for a fixed setting application. Okay, so again, if anybody has any questions, submit those via Shop Talk Live at millerwelds.com, and we can try to get those answered, whether it's in this session or in upcoming sessions. So encourage you to submit those, and we can try to get that answered. I'm going to keep moving along here. The next thing that we want to cover is the AC waveforms. So the Dynasty product that we have here today has 4 different waveforms. So the DX interface has 4 different waveforms. And we get a lot of questions about when would I want to use this. Again, I'm going to refer back to this, our quick reference guide. We have the 4 different waveforms listed down here in the bottom corner, and try to provide some guidance over when you would want to use some of those. I'm going to start off with the sinusoidal waveform, because that's fundamentally what has been used in a traditional sense. Just to make the drawing and the concept a little bit easier, I'm just going to make this a 50-50 balance setting. Not going to try to overcomplicate things and make the visuals a little bit easier to understand. So if this is a our AC waveform, sinusoidal type waveform. So our sine waveform here. When we talk about the different waveforms, one thing to keep in mind is that amperage is really what drives penetration. So we've already covered tungsten geometry. Balance is used for etching, etching or oxide removal. Our AC frequency is used for directional control. Amperage drives penetration, and I think it ties very closely with our actual waveform, and you'll see why in just a minute here. And that's because our peaks, or the time here, the distance up to here, our peak amperage in that AC waveform is really where we're getting a lot of that penetration from. Amperage drives penetration. I'm actually going to write it up here. Now, you can use other factors, and they'll have subtle effects on your penetration, but for the most part, this is going to be, in all practical purposes, the primary driver behind the penetration, our peak amperage. So if we look at the next waveform that you would maybe want to use, and I'm going to use blue because it's a very cold, or what I would consider a colder weld, used more for thin applications, and that's going to be our triangular waveform. So again, we still have the same amount of peak amperage up here, driving our penetration into the workpiece. But heat equals area underneath the curve. So we are actually, if that's how much heat we have in a triangular waveform, and in a sinusoidal waveform, we're actually adding all of this black area here. So you get a little bit more heat in sinusoidal waveform, still get the same roughly amount of penetration because our peak amperage hasn't changed, but you still get a little bit more heat. So for overlay applications, you know, you get that nice smooth transition up to our peak amperage throughout that AC waveform. You get more heat because we don't have as sharp of transitions. And by sharp of transitions, I'm going to draw the advanced square waveform now. What we would kind of call a harsh transition or fast transition is that true square waveform. Now, when we say a fast transition, we're going straight from 0 amperage up to our kind of welding amperage, or in this case, that, you know, I'm only drawing half of this just for representation purposes, but we have you know, up to our welding amperage, and so you're getting a significant amount of heat really quickly. You can see here in relationship to the triangular waveform, we have almost twice the amount of heat, or roughly twice the amount of heat going into the weld. You know, 1/2 base times height. A triangle versus rectangle, 1/2 base times height. You have twice as much area underneath the rectangle than you do on the triangle or the blue, which is our triangular waveform. So we have our advanced square waveform. The advanced square waveform gives you very fast heat input, very fast puddling, but one of the factors with the advanced square waveform is that harsh audible sound. When we have these fast transitions, it causes a rapid expansion and contraction of the gases, you know, in that plasma column, and that's where you get that buzzing or that audible noise from. So what we've done is we've also brought the soft square waveform. So we round these corners off slightly, not drastically changing the amount of heat input, but it does have a pretty significant difference on the noise level, because we're transitioning more smoothly as we get up to this high, you know, our high welding current or high welding amperage. And so from a welding perspective, that's going to be where I prefer to do it. That's where the factory defaults on, for example, the Dynasty product are, and has a much more appealing noise level as compared to maybe an advanced square waveform. So hopefully this helps cover when we might want to use some of the different waveforms and why you would want to use a couple of the different waveforms. Sinusoidal, generally used more for overlay or very high amperage applications where you don't want that harsh noise. You're still getting up, you know, doing a lot of heat input. If you have a lot of heat soaking in, you know, a lot of surrounding mass in your part, you maybe want to, you know, take a little bit slower approach to it. You got to preheat some of that with the actual arc as you go along. So you're going to be welding a little bit slower anyway. The sinusoidal waveform is good for those types of applications. The triangular waveform, again, lower heat input. We're taking roughly 50% of the heat out of the system, still getting those quick instantaneous hits at the peak amperage to help drive that penetration. So this is generally used for thin materials, because we're taking a lot of that excess or extra heat out of the system while still getting the penetration through. Oftentimes you can see a really good increase in travel speeds on, you know, say maybe 60,000 sheet or thinner by going to that triangular waveform. Soft square waveform, this is where I generally say, you know, roughly 1/8 inch material. That's going to be a good application all the way up through maybe about 3/8 of an inch. And then the advanced square, you can use that, you know, pretty much across the board based on your preference. You know, above 60 thousandths thick material, so a little bit above the triangular, all the way up through about that 3/8 mark. So it's going to have a little bit more harsh audible noise, probably allow you to travel just a little bit faster because you do get just a minute amount extra heat as compared to the soft square waveform. So kind of in summary of what we talked about. We talked about the balance setting, the tungstens, the frequency. We've also talked about the waveforms here. The last thing that we need to do is show you how to get into the different waveforms, and then we can go through and actually put some welding gear on here and run some demonstrations on some of the different theories that we talked about here tonight. So when we look at the actual front of the power source, in order to get into the different waveforms, similar to when we were getting into the tungsten sizes, we're going to use the A button or the amperage, and then our gas dig button here. So you see here, again, tungsten size is the first thing that pops up. We're going to use the amperage button, or the gas dig button, sorry, in order to scroll through here. And you see here, AC soft square waveform. So the AC soft, that's the one we just talked about over here on the piece of paper. The sinusoidal waveform, the triangular waveform. So if we're doing thin material, maybe I'll try demonstrating that. And then the advanced square waveform. So for today, we're going to leave it in soft square waveform and run it like that. Hit both the amp and the gas dig button, exits us out of the menu. So we're going to go ahead and put some safety gear on, safety glasses, welding helmet, and some gloves, and we're going to go ahead and get to doing some welding. So the large camera that you see, which is all black right now, is actually a darkened weld camera. So hopefully it will allow everybody to see quite nicely what we have going on here, and we can demonstrate some of the different things that we're going to be trying to show here and talk about. So the first example that I want to show, I'm going to go in here and I'm going to show some different balance settings. So I'm going to show a very low balance setting down in the 60 hertz range. And again, this is a lot of cleaning. So these parts here that you see on this plate, I haven't done any wire brushing on this, and that was intentional because I want to show the impact that balance can have. This material, it's been stored in a climate controlled environment, so it's not really dirty, but it does have oxides built up on the surface of it. It's not real clean stuff, but what we do want to look at is the cleanliness of the puddle. Hopefully you guys will be able to see as I weld along, there's not going to be any of that black oxides floating in the puddle. I'm going to weld about a couple inches across here. I'm going to stop. I'm going to change my balance setting up, which I'll explain. I'll probably go up to about a 95% balance setting. And then you'll be able to hopefully see some of those black oxides forming in the weld puddle and see what I'm talking about here. So I'm going to go ahead and put my hood down and start welding. So don't mind the buzzing noise. And then when we get done, we'll kind of explain what we see here. So for those that are maybe wondering what we're welding here, I'm just welding at 120 hertz, which is the factory default for the output frequency, using 1/8" aluminum sheet, and I've got 3/32 4943 filler metal here. You can see that welded out nice and clean, nice and even. Still have some of that oxide on the sides of the weld. I don't know if this will zoom in for me here a minute. If you can see that, so we got those that pretty wide etching zones on either side of the weld that kind of show us that we're getting adequate amount of cleaning action going on here. Now I'm going to go over here and I'm going to turn my balance setting up, and we're going to go up to about let's start at 90% electrode negative and see what happens here. Now, when I'm welding on this, it's going to probably completely eliminate this white etching zone next to the weld. It's also going to end up giving me some oxides in the surface of the material that looks like someone took a pepper shaker on top of my nice shiny weld puddle, and that's going to be those oxides floating on the surface that we talked about. So I'm going to put my helmet down, and we can go ahead and get started. Now you can see the weld is a little bit more so I can get this focused in for you here. The weld is a little bit more grainy than the first one that we did. So there's a lot of, looks like sand or pepper shaken in the top of the weld here. You also notice that compared to the first weld, had nice white etching zones. This one doesn't have those white etching zones. In fact, there's really non-existent. You can almost see a little bit of black, like right here next to the weld. Over here, there's a little bit of black next to the weld. And that's, that little bit of hydrocarbon that was trapped in the surface of the aluminum is for essence burning off or getting heated up and turning into that black soot that you see. And so this was 90% balance or electrode negative, and this is what I would consider inadequate amount of cleaning action. The entire time I was doing the weld, I could see those black oxides floating in the material, and this is 60%, so that was a little bit excess cleaning action. You get a lot of etching zones around the weld, and if we turn this back down to a 75% setting, that's going to put us right a happy medium between those two settings. The next thing that we want to talk about is the AC frequency. So I mentioned that using a higher setting will allow us to focus the arc. So if we do a low setting, like I talked about, that's going to give us a much wider arc and cause the weld to want to wander back and forth between two different areas there. So I've got this set to 75% balance, so our cleaning action is pretty much right where we'd want it to be. And then I'm going to go ahead and weld in here at a low frequency, and you'll hopefully be able to see the arc wander one plate to the other and not really drive into the bottom of the corner. I'm going to start putting a weld in. I'll weld a little bit just like before. I'm going to stop, and then I'll reset and turn my frequency up, and you'll be able to see the impact that has. So hopefully you could see from that, the arc was wandering the upper plate, turned the torch just ever so slightly, it wandered to the lower plate, and you know, that can cause some issues when you're trying to get the toes of your weld nice and straight. Now if we take and turn our frequency up, I'm going to turn this up, and I'm going to exaggerate this a little bit. In this 1/8 inch material, we probably don't need it quite this high, but I'm going to turn this up to about 180 hertz. Now, if I was working in my shop at home, I'd probably be, you know, in the 150 hertz range on 1/8 inch material. It's a pretty decent place where I'd like to weld this at. So I'm going to go ahead and put my hood down. You'll see that this is going to help drive that more into the bottom of that corner, help keep our weld toes nice and straight and even, and help us get nice stability in that T-joint. Now you can see that allows me to put a little bit smaller weld in there because I'm not fighting the arc as much, and allows me to get nice straight toes of the edges of my weld. And as we talked about, that's going to help us doing that smaller, more appropriately sized weld, especially on this 1/8 inch material, is going to allow us to have, you know, a little bit less distortion and allow us to get, you know, welds that are completed faster, reduce the overall cost for our business, less time, less shielding gas, less filler metal, and that's certainly critical to anybody that's, you know, in charge of a welding operation. Controlling that bottom line and our material spend, our labor spend is really going to be what, you know, helps your business succeed and drive forward. I'm not going to cover the different waveforms with on a demonstration. I don't think the cameras are quite good enough to pick up some of those subtle differences that you would see, but I think it's important. We went over it today. You can experiment with this on your own time with your own material and hopefully see some of those differences. So again, hopefully all this content was useful for everybody. If you have any additional questions, submit them via shoptalklive@millerwelds.com, and we'll try to, like I said, we'll try to get that stuff answered for you. And hopefully we'll see you next week when we talk about some of the more advanced stuff. We're going to be getting into independent amperage or independent waveform control, as well as touching briefly on, you know, the DC welding of aluminum. It's not very commonly done in the industry, but it is done in certain applications. And you know, hopefully you guys will be able to attend and visit and watch the live stream. And thank you, and have a wonderful night.